Hello, everyone. We are from the Visual Intelligence and Pattern Analysis Lab of Zhejiang University. We will introduce the paper called Generalization Matters, Loss Minima Flattening via Parameter Hybridization for Efficient Online Knowledge Distillation, which has published on Cvpr2023. Offline knowledge distillation technique aims to obtain a compact and effective student model guided by a large-scale teacher model for model compression. Based on the developments of knowledge distillation, the concept of online knowledge distillation is proposed to view all networks as students and achieve mutual learning from scratch through peer teaching, liberating the distillation process from the dependency on pre-trained teachers. Existing online knowledge distillation methods mainly encourage students to acquire diverse and rich knowledge, including aggregating predictions, combining features, working with peers, learning from group leaders, and receiving guidance from online teachers. However, these strategies focus on designing sophisticated architectures to exploit heterogeneous knowledge and enhance students' generalization, but they lack explicit constraints on generalization. It is known that a trained model is a point in weight space, and averaging multiple points leads to finding flatter minima in the loss landscape, such as stochastic weight averaging. Considering the multimodal setting in online distillation, we extend the average process to constructing a hybrid weight model, HWM, using the sampled convex parameter combination of peer students. Formally, we create an HWM in each batch during training, where T represents the TTH training batch theta HWM and theta M, M are HWMs and the MTH students parameters at the TTH training batch. M is the number of students, the RT is the weight vector. Dynamic sampling RT subject to alpha can achieve the following effects. First, HWM can fully explore the parameter points of the region around students by each batch sampling. Second, the concentration vector alpha can easily adjust the sampling probability of different points in this region. Unfortunately, HWM, due to the high nonlinearity of deep neural networks, directly hybridizing students' parameters can easily lead to the collapse of HWM. Therefore, we restrict the differences between students through intermittent fusion operations to ensure the high similarity of multimodal parameters and achieve effective construction of HWM. Here is the framework of our OKDph. Two students construct HWM by sampled convex parameter combinations in each training batch, and HWM's parameters are regularly fused with students. Two students and HWM's logits are obtained by feeding three types of data augmentations. As for optimization objective, we first synthesize knowledge in various scenarios by averaging the logits of each model, then, the holistic knowledge of the ensemble logits is further distilled into each student model by KL divergence. As mentioned in the previous section, the sampled HWM represents surrounding parameters in the space spanned by peer students. The HWM's classification loss for multiple consecutive training batches reflects upper and lower bounds on the loss in the region around students, hence we integrate it into each student's training to minimize the curvature of the region and flatten the loss landscape, enhancing students' generalization ability. The compared baselines include the mainstream methods of seeking flat minima and SOTA KD methods. Our method achieves high performance with few parameters. The SOTA baselines into both fields, with a single model's test time and convenience. Except for the flatness of the loss landscape, stability analysis of models is also the primary tool for measuring generalization. We evaluate the performance of several OKD techniques into context of noisy and limited data. Our method shows more robust performance mainly due to the regularization effect brought by our parameter hybridization. Also, we conduct the parameter sensitivity and ovation study. As for our contributions, first, inspired by the theory of multimodal fusion, we innovatively and traditional weight averaging to an on-the-fly stochastic convex combination of students' parameters called hybrid weight model, HWM. The supervision loss of HWM can estimate the curvature of the loss landscape around students and explicitly measure the generalization. Secondly, we propose brand new extensible and powerful OKD framework via parameter hybridization, OKDph, for loss minima flattening, which flexibly adapts to various network architectures without modifying peer structures and extra modules. It is the first OKD work that manipulates parameters. Thirdly, extensive experiments on various backbones demonstrate that our OKDph can considerably improve the student's generalization and exceed the state-of-the-art SOTA, OKD methods and SOTA approaches of seeking flat minima. Further loss landscape visualization and stability analysis verify that our solution locates in TH region having uniformly low loss and is more robust to perturbations and limited data.